I wanted to run through kind of the optimization strategy that I ended up landing on for the voxel engine because I thought it was pretty cool, pretty useful stuff. It gives us a pretty performant implementation of dual contouring. I'm not going to go into like the implementation of dual contouring itself or anything like that. This is purely basically some strategies I ended up landing on that got my engine to be performant. Um, so let's just do something like this, just so that we can kind of see what I'm talking about. I'm moving around, right? I'm flying around through space, and our engine is splitting our geometry and doing lotting and whatnot, and it works pretty snappy. Um, we can go pretty quick over the land while maintaining, good geometry up close. There's a few micro optimizations here that I'm not going to go over. Like we have a bit of a camera velocity based like look ahead on our lotting to try and make it keep up with the camera when we're traveling at high speeds and things like that. But all of that stuff is relatively minor compared to the major optimizations that are really the heart of what makes us able to actually run quickly. And I wanted to go over those today because they might be useful to somebody out there if they're working on something similar. So I did a little paint drawing to help visualize this. The first thing I'll talk about is basically how this works is it's meshing the surface of an SDF. What is an SDF? It's called a signed distance field. Basically, it's taking your closest distance to the conceptual, like math space surface of a function. It takes a point in space in as a sample, and it returns you the distance to the surface for that point. So, for example, if we sampled here, it might be like -6. In our case, I have my density positive. A lot of times the density will be negative. It doesn't really matter. What you really care about is the sign change. And there's a few things that change, like their ordering, depending on if you have negative density inside the surface or outside. In my case, I did it with outside, so that's how I've demonstrated here. So we have, this could be, say, -6 away from the surface, and this could be 4 inside of the surface, for example. Um, Now let's say we sampled the four corners of this box. We would have two negative and two positive. Because this box contains a sign change, we know that this box should contain surface. Um, so naively, you could just say, okay, well, we're only going to split nodes that contain sign changes. We're only going to allow those nodes to participate in lotting. But what you would end up with is a bunch of misgeometry and holes for the next conditions that I've drawn here. So here's one example. You have a object that's entirely contained within the node. The node, all four corners are outside of the object, so all four corners will have a negative value. And this would not be marked as a surface node. Likewise, here's another example. We have a peak coming into the node, but all four corners miss it. So what you would end up with is a hole, and then this wouldn't be rendered at all. Um, so we need a way better than checking sign changes. Jake, hush, come. Oh, he's gonna freak out. I think the mailman might be here. So we need a better way to do that. We need to be able to collect these nodes. Um, Anything with a sign change is a surface node. We know for sure it contains surface. But it's not guaranteed that a node that does not contain surface, does not have sign changes, doesn't have surface inside of it that would be revealed through subdivision. And we want to capture those nodes when we're splitting. We want to split as few nodes as we can, but we need to split every node that could contain surface. Um, so the first thing that we've got is this idea of a near surface filter. And we're going to take a look at what this would look like. So when we sample our nodes, we're already encoding this SDF distance in the corner density values. Maybe we can make use of it, as I've typed it here. So we would have distances for all of these internals, assuming that this is the closest surface to this corner. Then we would expect this corner to have some distance to the inside surface of the node. Likewise, over here with our peak, we have distance to the two corners up here, and then the closest distance to like the edge here. Um, so what is the largest distance that could be in one of these corners and the node still has the potential to have surface inside of it? Well, it turns out that it's a distance from the center to the corner. So the largest distance that the surface could possibly be from a node center while still being contained in the node would be equal to our center to corner distance. So if the minimum of the absolute value of each corner is less than the center to corner distance, the node could potentially contain geometry. So for a quad tree, it looks kind of like this. B near surface equals our t value greater than the minimum of the absolute value of every corner in the square. And then for the octree, it's the same thing, except for instead of 4 corners, we have 8. So what is the purpose of this? Well, we need to do several things as a part of our process. One of the major things we need to do is collect chunks. Hey, don't do that. Come. Come. We need to collect chunks at a specific depth in the tree that are going to be responsible for handling LOD and such. Hang on. 1 second. This guy's causing problems. Okay. Okay, come. Come on. Come back up here. Okay. So to collect those chunks, initially I was just exhaustively splitting the tree down to chunk depth, but that's expensive and slow. It takes a long time for our actor to spawn in because we have to do this recursive octree split down 4, 5, 6 levels deep. We don't want to do that. It's expensive, it's slow, and it's unnecessary. Hey! Stop. No! Hang on. 1 second. I gotta deal with this. All right, so recursively splitting down to chunk depth. What I was doing originally was recursively splitting the entire tree down to chunk depth, finding every surface node, and then finding every neighbor of every surface node and composing those into our chunk set. It's not great. We have to split the entire tree to do that exhaustively. We're just kind of brute forcing a solution to the problem. If we use this filter, though, we can have a much more elegant and robust solution that doesn't need to exhaustively split 5 levels of an octree. Instead, when we go and we are splitting nodes initially and splitting down to the chunk depth, we only split nodes that pass the near surface filter. That means that probably 99% of the nodes in the tree just immediately get discarded or not split, so we don't have to do any operations on there, and it's much faster. This is also used for like our regular lotting operations past the chunk depth. We will split any node that satisfies our LOD threshold requirements for needing to split that is also passes the near surface check. So yeah, this one right here alone is a huge speed up because this will cut out the majority of nodes that we need to process. The next thing we do, all right, so how do we get these density values into our corners? Well, we're sampling a signed distance function, and almost always that call to sample is going to be our most expensive operation in the hottest part of our loops. It has to happen the most out of any other thing we do, and it's the most expensive thing we do. So we don't want to sample a lot. We want to sample as little as possible. So let's think about the root node. If we spawn a root node, we need 8 samples. We have to sample our signed distance field 8 times to get the density values for each corner of the root node. So that would kind of correspond to the naive case. Whenever we split our node, each child is responsible on its initialization or constructor or something like that for sampling all 8 of its corner densities, plugging them into its corners. So for a quad tree, we would need 16 samples to do a split, and for an octree, we would need to do 64. This is ignoring the fact that we share geometry between all the child nodes. So, for example, every child node will inherit one corner from the parent. We don't need to recalculate these 8 points after we've calculated them the first time in the root, for example, because we've already calculated it and it can just become a part of the subdivided node. So let's take a look at the subdivided node here. Okay, so you can see here we still have our 8 red points on the corners that we inherited from the parent. We get those for free. Check. Free is good. We just directly inject these corner density values, positions, etc. into the child node top down when we do our split. Next, we have a point in the very center, the orange point. This is shared by all 8 nodes, and I'm realizing I missed a line here. Let's do this. This is shared by all 8 nodes in the split operation, right? So we only need to sample it one time. Each child node does not need to sample this same point over and over 8 times. We sample it once and we propagate it down to all the children. That eliminates 7 samples. Oops. 7 samples. Minus 4. Minus 7. Next, we have 6 face points that need to be generated. 1 center point for each face of the cube. Right? And each of those are shared by 4 nodes. So instead of each of these nodes, each of these points being sampled 4 times each, they're each sampled 1 time each. So we save negative, I think it would be 24. And then finally, the edges are sampled. Each edge point is shared by 2 nodes. So you'd have 12 times 2, negative 24. Oops. So if we had 64 initially, let's check if my math checks out. 48 plus 7 is 55 plus 4 is 59. And we had 64 before. Wait, no. I did something wrong. Regardless, you can see what I'm talking about from the diagram. I think I did my math wrong somewhere along the way. Oh, yeah. It's 24. It's negative 24 minus 6 because we had to do these 6 samples. So, like, this would have been 8 samples. We save 7. We save 4. Here, this would have been 24 samples, but we only have to do 6. So this would be, oops, nope. This would be 18. And then likewise here, this would be 24, but we only have to sample 12. So 12. And that should line up. So this is 40, negative 47, negative 51. Hey, buddy. Hey, buddy. Okay, my dog's decided that now is the time to climb on me. So the total number of samples we have to do under this paradigm works out to 19. I'm not like dogs climbing on me. It's very hard for me to draw the math. Um, if we were doing it naively, we would need to do 64. That's more than a 3x speed up in the amount of samples we have to do. And for a quad tree, it would be the same, except for you would need 5 samples per split instead of 16. So basically, you're always saving like a little bit more than 3x or like a reduction of about 3x in the amount of splits you do. The other nice thing about this is that we're using Fast Noise 2 library as our noise formula and has a simmed interface that can take a batch of points to process them all at the same time. Um, so since we're doing our splits from this parent level and pushing them down, we can compute our 19 points that we're going to need and then batch sample all of them in a single simmed call, which is better than making a bunch of individual calls or a call with 8 samples in the naive case per node. So it's much better. We're doing a third of the samples, more than a third, or less than a third of the samples, and we're doing them in a batched format that allows our us to take advantage of the speed of the noise engine that we're using. Okay, next up, we want to be able to represent planets that are larger than the Earth, and this kind of ties both into precision and it ties into performance as well. So the biggest hurdle for this is that our mesh buffers use their vertex positions as 32-bit positions. With 32-bit position, we cannot get close to an Earth-like scale before we are easily overflowing the bounds of like how of the precision of our mesh. So you're going to get like jitter and all this kind of stuff. So what I was talking about before about collecting the chunk nodes where we split down to a specific depth, only splitting nodes that are classified as near surface until we have the collection of near surface nodes at a specific chunk depth. So those form our chunks, and each one of those chunks owns a mesh component. We build the mesh for a given chunk in chunk local space. So that means our primary threshold for precision goes from the entire size of the planet to the size of our chunk. So our chunks need to be deep enough in the tree such that their size is small enough such that the mesh that chunk owns can be represented with 32-bit coordinates at an acceptable level of precision. No like jitter or anything like that. And then what we do is we take that mesh component itself and we position the component at the chunk center. And the component positioning is in double precision. The mesh verts are the only thing in 32-bit precision. We can position the components in full double precision. So basically, as long as our chunks are small enough to have the mesh component not exceed our precision thresholds, we can achieve very large scales. I can get to 8 to 10k kilometers before we start in radius, which is a lot larger than the Earth, before we start seeing precision issues. And the issues are no longer really, I think, at those stages. It doesn't seem to be like the mesh that's a problem anymore. It's the actual like Unreal Engine movement system for your character and things like that start like you're just too big. But we can get comfortably up to Earth scale. We can exceed Earth scale by 30-40% and be fine. Which to me, like, that's good enough. Earth scale is honestly impractical. I have the default set to 1,000 kilometers, which is much less than Earth scale. But it's big enough. Like, the Earth is a big place, right? So the fact that each chunk is controlling its own mesh and that we maintain a collection of near surface chunks leads into the last little primary part of the optimizations going on here, and that is async LOD. So we hold a collection of near surface chunks. We have to every so often on an interval, we have to check the camera position of the player, and we have to propagate that through an update LOD call, and we will do some computations against every node, every active node in the tree, every active near surface leaf node, and we will check that node. We will check to see if it should split or merge. It goes through a process like if it's split, if it's supposed to split, we split it. We do our 19 samples split from up here, and we populate those nodes. If it's supposed to merge, it will check with the parent to see if the parent should merge, and if the parent should merge, it will merge. Merging doesn't require us to do any kind of resampling, so I'm not going to go into that because merging is just intrinsically fast. We're not worried about that part of the process. It's really generating the new data that is slow, and that needs the optimization. So we're primarily concerned with like splits when it comes to performance, right? So why does chunking help us there? Well, because we have this collection of chunks at a specific depth that are going to have be managing like basically mesh lifecycle and all this good stuff, we can give each chunk its own thread to work with, and we can say go update your LOD. And because the chunks are non-overlapping, we don't have to worry about like any synchronization between other parts of the tree. We update the chunks. Each chunk updates its own LOD for all its leaf level near surface nodes. Then after it's done updating its LOD, if the chunk changed, it will repopulate its mesh buffers into a temporary buffer. And then finally, at the end of all that, it returns to the game thread and it swaps the pointer out from the real-time mesh component that's currently pointing at its current mesh buffer to point at the new mesh buffer that we just updated. And then we drop off the game thread. The only thing we have to do in that entire process that's on the game thread is swapping the mesh data buffer pointer, which is fast. We're not exhaustively populating the entire mesh buffer or anything like that on the game thread. It all happens on the background, and then when it's done, we go back to the game thread and we swap the pointer out to the new data, and then we regenerate the mesh and then bounce off the game thread again. So that is pretty much the largest performance improvements. There's a bunch of other, like I said, little micro optimizations and stuff in my implementation. But for all intents and purposes, if you do these things, it will be pretty dang fast. I think right now, let's see. See if we're getting any logs here. We don't get logs unless we're like taking unexpectedly long. So like there were some. We got several data updates here that were like slightly over 100 milliseconds, right? Which would be 10 times a second, which is still pretty quick. Output low? Any more? Yeah, so we're looking at somewhere, it usually seems, depending on how deep you are, how big your object is, like I think pointed actor is at what right now? 1,000 kilometers. It will range in the 30 millisecond per LOD pass to 200 millisecond per LOD pass, but usually not more than that. Obviously, I've kind of just glossed over the dual contouring algorithm. That's not really the purpose of this video. This is more about like the optimizations put in place to help with that. I've also glossed over like the fact that I said that, you know, we're sampling fast noise, but that's not the only thing we're sampling. We have a wrapper around it that allows us to add other layers. For example, our edit layer. is also in that process. So like if I drop in here, oh yeah, I can't do that unless I begin play. Sorry. There we go. So if I drop in here, and we'll just switch to unlit. Basically, we have a wrapper around our noise function that allows us to composite other things on top of it. And then we have an edit store layer that we can paint into. And the edit store layer is composited on top of the noise layer when we're sampling. So that's what allows us to like dig holes. Basically, we're drawing in a second SDF and then compositing the two together in order to do editing. Um, so we're not directly changing like the density values in our nodes themselves. We're changing the underlying density formula that our SDF is using, and then we are basically resampling the SDF in the nodes that were affected by the update to regenerate their geometry. Yeah, let's see the wireframe here. And there's all kinds of ways to there's a lot more to this than just those optimization methods, but those methods were the ones that really caused this to actually perform well. So I wanted to outline them. They might be helpful for anybody doing similar type stuff. The biggest two being the near surface filter, so that we don't have to unnecessarily split a bunch of nodes to get down to chunk depth. We don't have to do like neighbor crawling to find near surface node neighbors or anything like that. We just use the near surface filter. If you pass the near surface filter, you participate in lotting. If you don't, you do not. Pretty much it. And then the sample dedupe. This reduces the number of samples we do by more than 3x, which is obviously going to be about 3 times faster. The precision and scale stuff, this is more about like how can we get larger, or how can we get large enough to be like an Earth-sized planet without any black, like legitimately that large, not like faking it somehow or anything like that. Like no, it's legitimately as big as the Earth. We can get to that scale based on the fact that we build our mesh in chunk local space and then move the mesh component to be centered on the chunk. And then the async lot is the last thing. This is pretty box standard multi-threading. We want to do all of our LOD data operations off the game thread. That includes updating our tree structure, resampling our noise, and regenerating our mesh buffer. All of that happens off the game thread, and all of that happens independently for each chunk at the same time. Like we are allowing each chunk to process simultaneously, concurrently, those three things. And then when it's done with the LOD updates, which are tree structure changes, the resampling of corner data, and the regeneration of mesh buffers, we then kick off to the game thread for a split second to swap the pointer to point at our newly updated mesh buffer instead of our old mesh buffer, and then our mesh updates. So yeah, I mean, ends up being pretty short here, I think, but it's a quick and dirty overview of kind of some important optimizations I ended up making to make this actually work effectively at speed. I don't think that I can get too much faster than I am right now doing it on the CPU side. I do think that we're at, I'm not going to say the limit. I'm sure there's things that I've missed here. Um, but I think to get much faster than what I have here, you would probably have to move to like compute shader based stuff and integrate some like GPU compute into the pipeline, which I really didn't want to have to do because this is like I prefer it to stay simple the way it is. It's fast enough for me on the CPU, so I probably won't do that unless the compelling reason arises that would have me doing it. And yeah, that's pretty much it. That's how this thing works. We'll go ahead and do like a also never mind the bad textures or the bad materials and such. I've done very minimal work at this point on I've done very minimal work at this point on terrain materials on did he he unplugged my computer. No wonder it got slow all of a sudden. Jake, you unplugged me, you bastard. Okay. Yeah. So dog unplugged my computer. I was like, why is this chugging? Let me plug my computer back in. There we go. Yeah, if the computer comes unplugged, it will dramatically slow down. But yeah, that's pretty much it. We'll just do a quick, fly through of the planet, fly through some clouds here, fly over here, go down here. We can drop in. I might have dropped in a little too high. This level of speed is definitely enough for any kind of like walking around on the surface at human walking speed or run speed. The goal of the performance pass was to prep it to be able to support like spaceship level flight speeds. Um, so like, and we would do like some form of like speed limiting. Like once you get inside the atmosphere, we cap like how fast you could go in your spaceship and things like that to a reasonable amount. But I think this is fast enough to support that anyway. So I think we're good as far as performance goes on this piece of it. And pretty much everything I just described applies to both quad trees and octrees. I have all the same optimizations in the ocean quad tree that I'm using that we just described for the octree. They're just minus a dimension, right? For example, let's go take a look at the ocean mesh. We can actually turn this off. There we go. We also do some culling of the mesh generated by the ocean. We don't generate mesh that's deep under the surface. But the ocean mesh, is a quad tree, and it's operating with all of the same optimizations. It just works a little differently because it's 2D instead of 3D. But we needed a surface that we could basically apply a water shader to do, some wave displacement stuff. So yeah, that's it. Those are the major optimizations that I had to kind of bash my face on the wall and blunder my way into. And hopefully it's helpful to somebody. All right, later.